The Boltzmann factor is a fundamental concept in statistical mechanics, providing a simple way to understand how the probability of a system being in a particular state depends on its energy and the temperature of its environment. It is a thermal weighting factor that tells us the relative likelihood of a system occupying a specific energy state. Imagine a collection of particles, like molecules in a gas, constantly colliding and exchanging energy. Some particles will have high energy, some low, but what governs this distribution? The Boltzmann factor is key to answering this question for systems at thermal equilibrium. It helps us determine the probability of microstate occupation. At its core, the Boltzmann factor is about probability. It tells us that states with lower energy are inherently more probable than states with higher energy when a system is in thermal equilibrium. This intuitive idea is quantified by the exponential nature of the factor. Consider two states with different energies, say E1 and E2. The Boltzmann factor dictates their relative probabilities. Specifically, the ratio of the probability of being in state 1 to the probability of being in state 2 is given by e to the negative E1 over kt over e to the negative E2 over kt. This means if E1 less than E2, state 1 is more probable. Temperature, denoted by T, plays a crucial role. It sets the energy scale against which all other energies are measured. At very low temperatures, only the lowest energy states are significantly populated. As temperature increases, higher energy states become more accessible and thus more probable. The product Kt, where K is the Boltzmann constant, represents the characteristic thermal energy of the system. The exponential form e to the negative e over kt is not arbitrary. It arises from fundamental principles of statistical mechanics, specifically from maximizing entropy subject to constraints of fixed total energy and particle number. The exponential ensures that probabilities multiply for independent systems, maintaining a stable energy distribution over time through collisions. The Boltzmann factor is typically written as e to the negative e over kt, where e is the energy of the state, k is the Boltzmann constant, approximately 1.38 times 10 to the negative 23 joules per Kelvin, and T is the absolute temperature in Kelvin. The negative sign in the exponent means higher energy states lead to smaller Boltzmann factors, hence lower probabilities. To grasp this intuitively, imagine a staircase representing energy levels and marbles representing particles. If you shake the staircase gently, most marbles will settle on the lowest steps. If you shake it vigorously, marbles will reach higher steps more frequently, though the lowest steps will still have more marbles on average. The Boltzmann factor quantifies this distribution. This seemingly simple exponential appears across vast areas of physics and chemistry. It's fundamental to understanding reaction rates, as seen in the Arrhenius equation, explaining why reactions speed up with increasing temperature. It governs the distribution of particles in a gravitational field, like air density decreasing with altitude, and is essential in solid-state physics, chemistry, and even in fields like astroparticle physics. The Boltzmann factor is truly a universal exponential, a cornerstone of statistical mechanics. It provides a powerful and elegant way to connect the microscopic behavior of individual particles to the macroscopic properties we observe in systems at thermal equilibrium, making it one of the most important laws in statistical physics.